Welcome to my talk on solving large real-life bus driver scheduling problems with complex brake constraints. My name is Kletzander. This is work done in collaboration with Nysret Musliu at the Technical University of Vienna in Austria. So let's start by looking at the problem we're dealing with. What we want to do is we want to assign bus drivers to predetermined bus tours. So down here we can see an example with 8 bus tours. And each of those bus tours consists of different bus legs. So for example, for the first tour, we've got the bus legs in this table. They all have a certain start time, end time, start position, and end position. For example, the very first one starts at position 0, which is usually the bus depot, and goes to a station with index 5. Typically what we have here are the larger stations where drivers can get off the vehicles and can also take their breaks there. What we also given is a distance matrix. So this gives us how long it takes to change vehicle while staying at the same position, and also how long it takes drivers to change to a different position without actively driving a vehicle. So for example, when they leave a bus, take a break at a position, and then have to move to another position to take over another vehicle there. Now what makes this problem very complex is that it has a lot of complex constraints based on legal requirements and a collective agreement. So for any shift, basically we've got the bus legs, the larger boxes. There might be some working time before the first and after the last one. There's some idle time between the bus legs, and there might be passive ride time, which is changing to a different position without actively driving a bus. Now, one of the measures that we have is total time, simply the span between the very beginning and the very end of the shift. This is bound to a maximum of 14 hours. The next one is driving time, where all bus legs themselves contribute. This is limited to a maximum of 9 hours per shift, and regular driving breaks need to be taken after at most 4 hours of driving. Either 1 of 30 minutes, or 2 of at least 20 minutes, or 3 of at least 15 minutes. Then there's working time. Working time is basically everything that is paid. So that's everything except for certain idle times. One idle time that we've got is idle time with at least 3 hours. That's called a shift split. That's always unpaid, completely free time for the driver. However, that's very badly regarded by the drivers. Otherwise, we've got a maximum of working time of 10 hours. A minimum of 6.5 hours that is paid. So if a shift is shorter, still 6.5 hours are paid anyway. There's a required rest break with different lengths depending on the length of the total shift. That can be split again. One part has to be at least 30 minutes, the others at least 15, and the first part can be no later than 6 hours into the shift. Finally, there's the question, which of those rest breaks are paid or unpaid? The answer is, it depends. It depends on the positioning within the shift. So basically unpaid is only centered in the shift, not within the first 2, not within the last 2 hours of the shift. The maximum amount of unpaid rest depends again on the position of the 30-minute break. If this is centered, not within the first 3 or the last 3 hours of the shift, then there's 1.5 hours of unpaid rest. Otherwise just 1. Now that we've got an overview of all those complex constraints, let's look at a solution. For the solution, we actually still need an objective function. We could just optimize cost, but as we will see later, that's a very bad idea. So what we optimize is a combination of cost, total time, passive ride time, vehicle changes, and shift splits. So for our example from the beginning, this would be an optimal solution, using 12 employees to cover all the 8 vehicles throughout the day. Now, what we did in this work is first we did an analysis of the problem characteristics and how those compare with the objectives and constraints of the problem. We developed a new benchmark data set that we released to the public. We developed a solution method based on a construction heuristic and simulated annealing. And we deeply evaluated the employee satisfaction criteria and why those are necessary. Let's quickly look at, for example, the demand distribution. This is a typical distribution throughout the day for one of our instances. There's a very high morning peak, typically when everyone needs to get to work, a less pronounced evening peak, and some kind of a plateau in between. Now this completely clashes with the constraints that we have, because we want to have shifts of a minimum length. So short shifts here are expensive. Split shifts, where the driver has to drive part of his shift here and part of her shift here, badly regarded by the drivers due to the kind of useless long break in between. Another important aspect, waiting times. As we can see, for example, in Tour 2, there are a lot of idle times in the bus tour itself, where the bus is just parked at a final stop and waits for the next turn. Those idle times can ideally be used for breaks in the schedules of the drivers. However, not for full-length breaks, only for the split versions of breaks. So that's basically why it's important to consider all those split break options and not just long breaks. Regarding the benchmark instances, we've created a new instance generator, and we've published an instance set with 50 instances in 10 different sizes, ranging from 10 tours, so basically representing small line clusters that are in real life often used when bus companies have to compete for taking new lines, up to large ones with around 100 tours, almost 1,000 legs, which represents kind of medium-sized Austrian cities in their whole. Let's look at the importance of employee satisfaction. Up here we see the optimal solution for our first instance with the combined objective. Down here, when we just optimize for cost, we can reduce the cost by 3.3%, but every other objective is completely obliterated in this solution. Nobody would work that. So we can see it is very important to have an objective function that actually creates practically usable shifts. Regarding the solution method, we use a construction heuristic with 3 different steps. So first we assign bus legs to employees where the cost increases the least, also considering adding new employees. Then we assign as many consecutive bus legs of the same bus tour to this employee. And finally, we rebalance shifts because the construction tends to make morning shifts too long compared to evening shifts. So we shift some of those bus legs to the evening shifts. For improvement, we use simulated annealing, where the neighborhoods are swaps of either single bus legs or whole ranges of bus legs, where we use higher probabilities for shifts with high penalties so that we can eliminate those penalties. And we use it either with different temperatures in simulated annealing or with temperature 0 as just a randomized hill climber. So let's look at some of those results. As we can see, for the construction heuristic, run times are below 1 second for the smallest instances, still below 1 minute for the largest, while the results are still like a 1-digit percentage away from the best results. The employees range up to more than 130 employees for the largest instances. Simulated annealing and hill climbing produce pretty similar results on those instances, with simulated annealing slightly better for smaller instances. Now, obviously those methods cannot prove optimality, so that's why after this work we continued investigating exact methods using column generation. By now we know that 4 out of 5 of the best results of simulated annealing for the smallest size category are actually optimal, and there's typically a gap of between 3 and 5% for the medium-sized instances. We also applied our method to a real-life problem with slightly different constraints with more than 2,700 bus legs and got a 4% improvement compared to previous human expert solutions. We also applied our method to a very different problem from Brazil by trying to compare to other results in literature, and could also improve 4 out of the 10 instances there. So to sum up, here you can see a summary of the main contributions of our paper, and thank you for your attention, and I'm looking forward to your questions.